I wanted to take you through the first video when it comes to preparing you for your Chemistry Paper 1 exam, which is obviously coming up over Easter. Here is the first booklet we're going to go through. That booklet is also available on the Classroom. We're starting off with the very first topic you would have looked at when we first started Chemistry GCSE, which is the structure of the atom. And that's where we're going to begin. So I want to start off with looking at the basics. So you often find these types of questions on the foundation to your combined science paper and also the foundation to your triple science paper. It is essentially we're making sure we know the definition of these 4 words, so atom, element, compound and mixture, and being able to identify those from diagrams. As you can see, I've got several diagrams within the booklet. So it's important we know and we're able to define what those words mean. So we'll start off with atom, okay? So the definition of an atom, I'm just going to quickly zoom in a bit to make sure the focus is fine. The definition of an atom is one particle, okay? And we would have looked at the structure of an atom as well, which we know looks a little something like that. And we'll come to talk about the parts of the atom and how each part is involved when we come to look at this later in the booklet. And elements, okay, so element is next. Now, generally, you will find them on the periodic table. Okay, so if it's on the periodic table, it is an element. It is usually one type of atom. And the way to spot an element, for example, in a formula, so let's say, for example, I've got the formula NaOH, you want to be looking for capital letters. So the capital letter tells you you've got an element. So here you can see I've got 3 capital letters, so therefore I would have 3 elements. And if I'm looking for this as specifically in a diagram, I can see that I've said that an element is one type of atom. So you can see in picture F, there is only one type of atom present, so therefore it would be an element. The same for picture E. This is what we call a molecule. So we've got 2 of the same element together. So that could be, for example, oxygen, which we know exists in pairs. So it's still one type of atom, so therefore would be an element. A compound is usually when you have 2 or more elements chemically bonded together. Okay, and compounds usually have 2 names. So for example, carbon dioxide would be an example of a compound. They're also not easily separated because they're chemically bonded together. And as we've said, it's 2 or more elements. So again, if I was looking at my diagrams here with the different pictures of representing these 4 things, I can see quite clearly in picture A, you've got 2 different elements that are chemically joined together. So that would be an example of a compound. And in picture D, you can see you've got 3 different elements there. Again, would be a picture of a compound. And then the final word we've looked at, or we're looking at, is a mixture. Okay, and this can be easily separated. Okay, so for example, the air is an example of a mixture that can be easily separated, and it's usually made up of elements, compounds, or it could just be compounds, but the key to this is knowing that it's 2 or more. Okay, and if you look at a picture here, you can see, for example, in picture B, you can see I've got 2 elements there. Here's one element there and an element there. So that would be an example of a mixture. Same with picture C. You can see from the picture, I've got one compound there, and I've got an element, and that also would be an example of a mixture. The key thing is knowing it can be easily separated, and the air is a good example of a mixture. We also look at crude oil in paper 2, and that's also an example of a mixture. Okay, so moving on from that, we would have then looked at with you this idea of chemical equations and being able to take what is text and turn it into a chemical equation. So we're going to go through the basics of what you'd expect, certain language, certain keywords that you would use when it comes to describing chemical equations. So I'm just going to do a chemical equation where I've got A, and I'm going to put little symbols next to this, plus B, again, little symbol, goes to give us C, in this case that, plus D, and in this case that. Okay, so here is your typical what we'd class as an equation, a chemical equation. And on the left side of the equation we have what are our reactants. So these two are reacting together, and the arrow shows that it's them making these two things here, which we call our products. And it's important we're able to recognize that for any symbol equations, for example, you will have these things in brackets, and that is telling us the state of the specific things that are reacting. So S equals solid, and it's important you notice the S symbol when it comes to things like precipitates. L equals liquids. G equals gas. And again, gas comes up quite a bit when we're looking for things like conservation of mass. Why don't we have the same mass on each side? Well, gases can obviously escape, so it's important we're able to recognize the gas. And then AQ, which stands for aqueous, which means you've got something dissolved in water, for example. And your acids, alkalis, salt solutions, they're all examples of aqueous, and AQ comes up in electrolysis, which is in paper 1. Okay, so what types of things do you generally get asked? This is for combined and triple science. You may be given text. So for example, here we've got a question that says methane is reacting with oxygen to make carbon dioxide and water. And it then says to you, can you turn that into a symbol equation or a word equation? So we'll do both. So I can see I've got methane reacting with oxygen, and that must be your reactants. So we've got methane plus oxygen, because we're saying it is reacting with oxygen. And the question quite clearly says to make carbon dioxide and water. Okay, so carbon dioxide and water. And if I was going to then do the symbol equations, I know from alkanes, alkenes, that meth means one carbon. So CH4 would be the formula for methane. Oxygen is a non-metal, and most non-metals come in pairs. So we'd have oxygen like that. Carbon di means 2, so CO2, plus water, which is H2O. Okay, and this is actually a combustion reaction, which you would have looked at for chemistry paper 2. And again, you may be asked to balance equations in paper 1, and it's important to remember that they will in fact put lines next to where they're expecting the numbers to go. So the way I always balance equations is I do a dotted line down the arrow, and I work out how many of each elements I've got. So C, I've got 1 carbon over here. Over this side, I've got 1 carbon too. So those carbons are happy. H's, I've got 4. And over here, I've only got 2. So they're not happy. I need to sort those guys out. And oxygens, I've got 2 atoms here. And over here, I've got 2 plus 1, which gives me 3. So again, they're not happy. So to balance this, the rules are quite simple. You can only add big numbers at the front of the formula. You cannot add little numbers or in between numbers. It can only go at the front. But as I said, they often give you the lines in front of where you'd expect the numbers to go. So here I've got 2 hydrogens. Over here I've got 4. So how do I make 2 become 4? Well, I want to therefore double the number of hydrogens. So I put a big 2 in front. That now gives me 4 hydrogen atoms. But now I've changed the number of oxygens. So here I've got 2 oxygens and here I've got 2 oxygens. So that gives me 4 oxygens now over here. But as you can see on my reactant side, I've only got 2. So I'd have to put a big 2 there in front of that. I will say about 75 to 80% of the time, the answer is often a 2. But it's important that you're able to break it down just like I've done here. Okay, what we then went on to look at is this idea of separating out mixtures, and it's important that you are able to do that and break that down. Okay, so what we're going to look at first of all is this idea of filtration. So filtration is usually used to separate an insoluble substance. Okay, so that, for example, is something that does not dissolve in water. Sand water, for example, is a good example. We talk about filtration in chemistry paper 2, but it is important you are able to label this. I've seen a 3-mark question come up where they get you to label the equipment. So it's important you know what they're all called. So we've got our funnel, our filter funnel there. Inside of that, you then have your filter paper. And that goes into a conical flask, where we've then got the insoluble substance gathering in the filter paper, allowing the liquid form of the mixture to then pass through, and you can then collect it. So it's important you know the equipment. It's important you know it's to do with insoluble substances. So for example, salt solutions, if it was an aqueous salt solution, that would be a soluble solid dissolved in the water. They would in fact pass through, and that's because they're too small and cannot be stopped by the filter paper. Okay, you've then got distillation. So this is distillation. And you need to be able to describe what's happening in the distillation process. I've not yet seen a question where they've asked you to label equipment, but it is important you understand what's going on. So usually used to separate 2 liquids. Okay, so for example, we could have inky water here. So we've got the ink and we've got water present. You can see from the diagram it is sealed, so no gases can escape. This here is what we call our condenser. Okay, and that we'll talk about that when we talk about the process. And then we collect our sample, as you can see in the conical flask just there. So from the diagram, you can see that we use the Bunsen burner to heat up our mixture. As I've said, that mixture here is inky water. And it then heats that, and depending on the boiling points of the liquids, whichever one has the lower boiling point will in fact evaporate first and leave as a gas. So as you can see, the gas will try to escape because that's what gases try and do, but because it's sealed, it is then forced down through the condenser. Now the condenser is cool, okay, so it will in fact turn the gas that has just escaped back into a liquid. And we can then collect that liquid here, which we've then essentially separated the mixture based on the boiling points of what is evident. And this comes up quite a lot in paper 2 when we talk about fractional distillation, alkanes, alkenes. So it is important you know what's happening and where. So it's all to do with boiling points. We heat up the solution, the lower boiling points evaporate first, tries to escape, can't, so therefore is forced down through the condenser, which is cooling it from a gas, turning it back into a liquid, and we can then collect our liquid samples there. We've then got crystallization. Okay, so crystallization, you can see that we've got, usually it is about separating a solid that is contained within the liquid, so it's dissolved within the liquid. So we often find it in salt solutions. And in chemistry paper 1, you have to be able to describe how you make, how you extract salt from an insoluble base. So essentially in here you've got your salt and you've got water, and that is obviously a mixture. And we want to get our salt crystals evident so we can actually look at them and weigh them, for example. So to do that, we would evaporate. So the key thing here is knowing to evaporate the mixture. What that does is it will allow the water to escape, leaving behind the salt crystals. Those crystals, you can then either leave them to dry, or you may use filter paper to remove excess water. And that will then allow you to extract your dry crystals, which you might then want to reweigh if it was looking at mass, for example. So the key thing for crystallization is evaporating the liquid, leaving behind the salts. We then have to leave to dry, and then we can remove any excess water by dabbing with filter paper, and then we get our dry crystals formed as a result. This here is fractional distillation, which is in paper 2. And again, it's very similar to this here, but it's to do with a mixture of hydrocarbons. And if you watch the video on alkanes, alkenes, and property of carbon, oil, crude oil, for example, it goes into detail with that there, but it's very similar to that of the distillation diagram we've just gone through. So they're the basic skills that you need to have prior to starting the GCSE content. And we're now going to go into the model of the atom, the structure of the atom, and essentially the key things that you need to be aware of. So we're going to look at how it was, or how it is, that we've actually been able to develop the atom structure that we have today. So as you can see, I'm drawing the structure of the atom that we are all taught in chemistry, and you need to be able to explain how we got to this model that we have today. And there are several people who have been involved in that, and we're going to look at each of the things there. It also talks a little bit about how theories change based on new evidence, and it's important that we're aware that theories do change as new evidence comes along, because it changes the way that we think. So we'll start with Dalton. Again, I've not seen much come up on Dalton. Just to be aware, he was kind of the first person who came up with this idea of atoms being tiny particles, okay, that have a solid sphere. So spherical in shape, this idea like that. And he was the first person to kind of come up with this idea of this atom being tiny. Now, the one that they often get you to look at in detail is the plum pudding model. Now, I don't know about you, but I can honestly say in my 41 years of existence, I've never had a plum pudding in my life. So I often get people to think of this in the context of a muffin, a blueberry muffin, which will hopefully explain it as we go through. But what usually comes up in regards to plum pudding is you often get a comparison between this model here and how it is similar and different to the model that we have today. So it's important we understand the plum pudding model in detail. And as you can see, it was Thomson who proposed the plum pudding model. Sometimes you can see it as a diagram that looks like this. I've seen it where they put the big plus there and then they have negatives around it. It's very similar. Well, it is exactly the same, but just be aware that you might see it like that as well. So we'll go through the plum pudding model. So I want you to imagine a muffin. This is where my GCSE art pays off. And if I take a blueberry muffin and I cut it in half, what I will see in that muffin there is the cake, the dense part of the cake with the blueberries stuck in. And that's similar to plum pudding, where the dense part of the cake actually is our ball of positive charge. And that is dense, so nothing could pass through it, but it's made up of this ball of positive charge. And we know that that is in fact protons, okay, and that is what we know as the positive part of the atom. And then stuck into that ball of positive charge, we have got our negative charges, which is our electrons. Now, at the time, we knew about those, so just be aware. So on the model of my blueberry muffin, the blueberries here are the electrons, okay, which we know are negative. So you can see that it's very similar to that of a plum pudding. We've got our dense object with our ball of positive charge with those electrons stuck into it. And the model that we have today, though, is slightly different. And there's a really important experiment, Rutherford's experiment, that actually allowed us to break this model down. So as you can see, I've got my nucleus. So this whole thing in here is what we call our nucleus, which is made of mass, so dense, and also has a positive charge, which we know are protons, and they sit inside the nucleus of the atom. We've then got a large amount of space, so you can see there's lots of space there between the shells. And then we have our electrons, which are on the shells. So quite different to the model that was proposed by the plum pudding model. So how are they similar? Okay, and how are they different? And it's important you're able to articulate that. I've seen it come up as a 4 marker on a higher paper. I've seen it come up as a 6 marker. It's important you're able to be able to describe the differences between each of the models. So we'll talk about how they're similar. So we can see they've got a positive charge. This also has a positive charge. So we've got protons, positive charges, evident within both models. We can see that they're spherical in shape. Okay, circular shape. You can see they also contain negative charges. So you've got the electrons there. But essentially, that's really all it's got in common. Okay, so which we know are electrons here. So in terms of differences, you can see in the plum pudding model, or the blueberry muffin model, as I like to call it, that actually it's dense, so there's no spaces, whereas here you can see quite clearly there's lots of space. So plum pudding model is dense, no space, whereas the current model of the atom has lots of space between the nucleus and that of the electron. Also, where in this model here, you can see that actually the dense part of the atom is in the center and the nucleus. So the nucleus is dense, so has mass and positive charge. Whereas in the plum pudding model, the whole thing was a ball of positive charge. Okay, so plum pudding is different because the whole of the cake part essentially was a ball of positive charge, which we know actually the positive charge sits in the nucleus. In terms of electrons, so in the plum pudding model, you can see the electrons are all stuck in, whereas in the structure of the atom, we know electrons are arranged on shells. And that was down to Bohr's work, which we'll come to look at in a sec. So there are your key differences. The plum pudding model had no space because it was dense. Your structure of the atom had spaces within it, as you can see between the nucleus and the electrons, there's lots of space. The nucleus was positively charged, whereas in the plum pudding model, it was a ball of positive charge. So again, that's a difference between the two models. And our electrons were not stuck in randomly. Actually, they're arranged on shells, and that's another difference between the two. Now, as I said earlier, there was a specific experiment that allowed us to work out that was indeed the structure of the atom that we have today, and that was Rutherford's experiment. And again, I've seen this come up as a 4 marker where you've got to be able to describe what Rutherford did. He actually won the Nobel Prize for this experiment because it allowed us to get the model of the atom that we teach you today, which is that model there. And you need to be able to describe what his experiment showed and how it helped to disprove the plum pudding model. So we can see we've got what looks like a complicated experiment, but actually it is quite straightforward. We've got our radioactive source here, which is alpha radiation. Now that comes from physics, paper 1, I think. But alpha radiation, you need to remember that alpha radiation is a helium nucleus. And a helium nucleus, if it's the nucleus of the atom, then we know it's got protons, which are positively charged, and it has neutrons, which we know have mass. And essentially what they did was they took alpha radiation and they beamed it into gold foil. And the gold foil was 1 atom thick. And something strange happened. We actually got what's called scattering. So often you find this experiment is called the scattering experiment. So you can see that the alpha radiation is scattering, and we're going to talk about the ways in which it's scattered and why. So to do that, we're going to draw a diagram. So I'm going to draw a diagram here just to break this model down for you. You can see here is my gold leaf, my gold foil, which is 1 atom thick. And what they then did was they took their alpha source, which we know is positive and has mass, and then 3 things actually happened to it. So we're going to look at each of these in turn. And hopefully that will help to then explain why plum pudding was disproved. So number 1, as you can see, that actually quite a lot, in fact, the vast majority of the alpha radiation passed straight through. Okay, so most of it, this is all number 1, most of the alpha radiation passed straight through. Now, what does that tell me about the atom? Well, it tells me there is space. So we know from plum pudding that plum pudding was dense. If in fact that was the correct model of the atom, we would expect to see none of the alpha radiation passing through. But as you can see from the experiment, the vast majority did. So that told us that most of the atom is in fact made of space. So it allowed us to say, well, actually plum pudding mustn't be correct. In addition to that, what we also saw is we got this slight deflection away. Now this happened when the alpha radiation actually got really close to the nucleus. Okay, now we know from today's current model that the nucleus is made up of protons and neutrons, and protons are positively charged. Now, alpha is also positively charged. So when the alpha radiation came very close to the nucleus, well, likes and likes repel. And this here is repulsion. Okay, so essentially 2 positive charges have been brought close together. So as a result, the alpha radiation repelled away from it and deflected away. And that told us that actually the positive charge must be in the central part of the atom, in the nucleus. Not the ball of positive charge we'd expect. In fact, it was only in the center part. Okay, so in the center part of the atom must be positively charged because we've got this repulsion. And then the final conclusion we could make from this experiment was if the alpha radiation actually hit the nucleus, we got reflection going on here. And as you can see, it's reflecting back out. Now, what does that tell us about the structure of the atom? Well, if you take 2 substances that have mass and you hit them together, you're going to get reflection. So we can see from this experiment that because alpha radiation has got mass, and we know the nucleus is made up of protons and neutrons, which have mass also, if we bring 2 things that have mass, they will reflect. And I'll show you that as a little demonstration. Here is an object that has mass. Here is another object that has mass. If we hit them together, you can see that actually it reflects and bounces off. So what does that tell us? It tells us that the nucleus was made of mass, that actually had mass. And again, that disproved plum pudding, because in the plum pudding model, they proposed that the whole thing was dense and the whole thing had mass. when in actual fact, we only got that reflection off when it hit the nucleus part of the atom. So it allowed us to work out that the nucleus itself must have mass. So Rutherford's experiment, although it looks complicated, actually allowed us to work out the structure of the atom that we have today. And it's important, if you're describing it, you have to link it to these three things. The key is remembering that alpha is positive and has mass, which is why we get the deflection and why we also get the reflection kicking off there for number 3. And then the final thing you need to know about the atom is the work of Bohr and Chadwick, and you only need to know what they did. So for example, Chadwick, he is the person who discovered the neutron. And I've only really seen Chadwick come up in a ticky boxy question where they give you the list of scientists, and you need to remember that he is the person who discovered the neutron. And Bohr, he is the person who proposed the idea of electrons being arranged on shells and put together the rule. So we know 2 electrons on shell 1, 8 electrons are the maximum on shell 2, 8, and then it only goes up to 2 for the last shell. So Bohr's experiments, he basically put together the model that we use today for electronic structure. And we'll go into the structure of the atom and electronic structure in our next video. Thank you.